Welcome to Morphic Labs, and today we're going to be discussing advanced correlation for markets. More specifically, we're going to be talking about random matrix theory and correlation matrix denoising. But before we get into that, do me a favor, hit the subscribe button if you want to keep up with more content like this. I would greatly appreciate it. And if you're interested in increasing your market intelligence, which if you're into trading on markets in any capacity, you should be interested in increasing your market intelligence. If that sounds like you, I have a free market microstructure and trading systems course that will walk you through the foundations of market structure, the mechanics of trading, market data, and analytics. And if you're a data nerd like me and you want to look at markets from different angles, I have a free advanced market aggregation course that will walk you through advanced price-based aggregation, volatility-driven aggregation, information theoretic aggregation, order flow microstructure aggregation, event-driven and hybrid methods, plus implementation and selection criteria so you can pick the most optimal aggregator for your specific use case. If you found that interesting, the links are in the description. Just sign up to be a free member and get both of these resources all to yourself for free. Now let's get into the technical detail. Random matrix theory and correlation matrix denoising. Financial correlation matrices estimated from N assets using T observations contain substantial noise when N over T is non-negligible. Random matrix theory provides the theoretical framework for distinguishing genuine correlation structure from estimation noise. 3.1, the Marchenko-Postler distribution. I'm probably butchering these names. If you're watching this, I apologize. Consider a matrix X of T independent observations of N independent random variables with zero mean and unit variance. The eigenvalues lambda, the corresponding correlation matrix, follow the Marchenko-Postler distribution in the limit n as t tends to infinity with q equaling n over t fixed, where p sub np of lambda equals q over 2 pi lambda times the square root of lambda sub pi difference lambda times lambda difference lambda sub minus, where lambda sub plus minus equals 1 plus minus the square root of 1 over q squared. Define the support of the distribution. Eigenvalues falling within the closed interval lambda sub minus and lambda sub plus are indistinguishable from those of a random matrix and thus represent noise. Reference 19 and 24 independently demonstrated that approximately 94% of the eigenvalue spectrum of empirical financial correlation matrices lies within the Marchenko-Postler bounds. Only a small number of eigenvalues typically corresponding to the market mode and a few sectoral components carry genuine correlation information. This finding has profound implications for portfolio optimization. And here are some empirical findings. Analysis of the S&P 500 correlation matrix from 1990 to 2020 reveals 1. The largest eigenvalue lambda sub 1 approximately equals n over 5 corresponds to the market factor. 2. 5 to 10 eigenvalues represent sectorial clusters. 3. The remaining 480 plus eigenvalues are consistent with random noise. This implies that naive sample covariance matrices contain approximately 96% noise, right? 3.2 Eigenvalue clipping and portfolio application. Several denoising procedures have been proposed. The simplest eigenvalue clipping replaces all noise eigenvalues with their common mean while preserving the eigenvectors, where lambda sub I equals lambda sub I if lambda sub I is greater than lambda sub plus, otherwise it equals lambda sub noise. More sophisticated approaches include shrinkage estimation, where the sample covariance matrix is regularized toward a structured target. LeDroit and Wolf derived the optimal shrinkage intensity analytically, minimizing the Frobenius norm between the estimated and true covariance matrices. The Prado, reference 7, extended these methods for financial machine learning applications, introducing techniques specifically designed for n greater than t regime common in portfolio management. And down here we have a table that will give us some data insights. And essentially, we have 4 columns. We have method, we have out of sample sharp, and we have turnover and maximum drawdown. And as you can see, sample covariance had a out of sample sharp of 0.42, a turnover of 285%, and a maximum drawdown of negative 38.2%. Eigenvalue clipping had an out of sample sharp of 0.78, turnover of 142%, and a max drawdown of negative 24.7%. LeDroit Wolf shrinkage had an out of sample sharp of 0.85, a turnover of 118%, and a max drawdown of negative 22.1%. Nonlinear shrinkage had an out of sample sharp of 0.94, a turnover of 95%, and a max drawdown of negative 19.8%. And essentially, what this data is implying is that you should stop using covariance matrices for correlation analysis or correlation measurements. Okay? The advantages: mathematically rigorous noise identification. Number 2, substantially improves portfolio optimization. Number 3, reduces ill conditioning of covariance matrices. Number 4, computationally efficient post-eigen decomposition. The limitations: number 1, assumes an asymptotic regime, finite sample corrections needed. Number 2, clipping threshold sensitive to Q equals N over T. Number 3, destroys trace preservation unless renormalized. And number 4, may remove weak but genuine signals. And that's about it for today. In the next video, I'll be discussing time varying correlation, right? And this is one of my most favorite correlation methods. I'm going to be writing some code for this somewhere this week. So yeah, expect this. And if you're interested in increasing your market intelligence, which if you're into trading on markets in any capacity, you should be interested in increasing your market intelligence. If that sounds like you, have a free market microstructure and trading systems course that'll walk you through the foundations of market structure, the mechanics of trading market data, and analytics. Plus, if you're a data nerd like me and are interested in looking at markets from different angles, I have a free advanced market aggregation course that walks you through advanced price-based aggregation, volatility-driven aggregation, information theoretic aggregation, order flow and microstructure aggregation, event-driven and hybrid methods, plus implementation and selection criteria, so you can pick the most optimal aggregator for your specific use case. If you found it interesting, the links are in the description. Just sign up to be a free member, and you have both of these resources all to yourself for free. And that's about it for today. I'm out. Bye.